So I'm going to talk a little bit about what it means for a set to be closed under an operation. And the first thing we have to remember is what a set is. And they have all these different names, and this should be a review, but let's talk about it again just so we know what we're talking about. Natural numbers are the ones you learned as a child. They started at 1, 2, 3, 4, and then on to infinity. Whole numbers are just like natural numbers, except for you have a 0. And again, they go on to infinity. Integers are whole numbers that include the negatives of all the natural numbers. They go to infinity in both directions. So oftentimes you'll see a Venn diagram type thing of all the numbers put together. So there, whole numbers are a part of integers. So integers is a much bigger set than whole numbers, and natural numbers is a part of whole numbers. So we started with the smallest set, which is natural numbers, moved up one step to whole numbers, moved up another whole step to integers, and now we're going to talk about the difference between rational numbers and irrational numbers. So the definitions of these are pretty straightforward, but maybe a little bit confusing. So a rational number is any number that can be written as a fraction. So if you think about that, as examples, obviously 1/2, but also 2, because you can write 2 as 2 over 1. So any fraction that you think of, whether it's a normal fraction or an improper fraction, or integers, are all considered rational numbers. So the rational numbers gets really, really big. An irrational number is any number that cannot be written as a fraction. And so that's a little bit harder to think about. And these are two separate things. The famous one is pi. And anytime you see a square root that cannot be simplified, that would also be included into your irrational numbers. Now just be careful, because the square root of 9 would be a rational number, since the square root of 9 is 3, and we can write 3 as 3 over 1. So there's some other irrational numbers. Another famous one is e, that we'll end up talking about later on. And then you can make some up, and a way that people remember it is any non-repeating, never-ending decimal is also considered an irrational number. So all of these, rational and irrational, are considered real numbers. And so as of today, the biggest set of numbers that you know are the real numbers. And then, we kind of work backwards through them. Real numbers can be split between rational and irrational. The rational numbers can be broken down into integers, because remember that integers can all be written as a fraction. You can break integers down into just the whole numbers by removing all negatives, and then natural numbers can be inside of the whole numbers. So a set is closed under an operation if, when the members of that set are used with that operation, the resulting number is still a member of that set. So I know that's a little bit confusing. So let's just think of integers first, and let's talk about adding and subtracting integers. So, for instance, if integers are closed under the operation of addition, then every time we pick two numbers, the result is an integer. So, just think of a couple examples here. Is there any way that we can pick two integers, add them together, and not get an integer? And so the answer is no. Every time you do that, you get an integer. So integers are closed under addition. So what about subtraction? Is there any two integers that you can think of or use that when you subtract them, the answer would be not an integer? And the answer is, again, no. So not only are integers closed under addition, but they're also closed under subtraction. So same thought process with integers. Can you think of any integer or any two integers that when you multiply them together you get something besides an integer? And again, the answer would be no. Right? Every time you multiply two integers together, you're going to get another integer. So it's closed under addition, subtraction, and multiplication. So what about division? So you can definitely pick some integers that when you divide them produce another integer, but for a set to be closed under that operation, it has to work every single time. So, I can pick an integer like 3 and divide it by 4. That's not going to produce another integer. It's going to be a decimal. So, in fact, integers are not closed under division. So here's two statements for us to consider, keeping in mind what closed means. If you add two rational numbers together, the result will either always be rational, sometimes rational, or never rational. Okay, so again, rational means it looks like a fraction, or could be written as a fraction, including integers. So we can get the never rational out of the way right away, because we can just pick one. We can just pick 1 plus 2, and that gives us 3. So right here we have a rational number plus another rational number, and it's equaling a rational number. So let's get rid of this one right off the bat. Okay, so now we're down to always rational or sometimes rational. So again, all rational numbers can be written as a fraction. So the next question would be, if we do 2/3 plus 7/3, we would get 9/3. And even if that didn't simplify into 3, it would still be a rational number. So clearly sometimes. So we've gone through integers. We've gone through an example of what fractions would produce. And so let's try the combination of the two. So how about 2 plus 7/8? Well, 2 plus 7/8 would be 2 and 7/8. You could change that to an improper fraction if you wanted. So that'd be 16 plus 7, so 23 over 8. And sure enough, that produces another rational number. So we've covered all our bases. We used any combination of rational numbers, integer and integer, two fractions, and a fraction and an integer together. And we can say that it will always be rational when you add two rational numbers together. So let's look at this next statement. If you multiply two rational numbers together, the result will be either always rational, sometimes rational, or never rational. Well, again, let's get rid of the never rational right off the bat, because we can say 2 times 3 is 6. And so right away, we just multiplied a rational number times a rational number and got a rational number. So there's no way this statement can be true. So let's go through the same kind of process. What about if we multiply two fractions together? Well, that would be 14 over 9, and so that would still produce a fraction, and so that's still rational. And then the other option would be to do an integer times a fraction, and that is just 14 over 8, and of course that can reduce, but it doesn't really matter for this statement. So there's no way we can come up with two rational numbers, multiply them together, and get anything except another rational number. So you would say that rational numbers are closed under addition and closed under multiplication. So now I'm going to throw a little wrinkle at this and try to cross two different sets together and see what happens. So if we add a rational number to an irrational number, the result will be one of these three things. And so let's make something really simple. Let's just say 1 plus the square root of 2. Well, we can't combine that any further. It's kind of like they're unlike terms. And so the answer to adding 1 plus radical 2 would actually just be 1 plus radical 2. And since we have this square root of 2 in there, it's got to be this sum has to be irrational. So the answer would be C, never rational. And so let's think about multiplying. So if we take a rational number and multiply it by an irrational number, the result would just, in this case, for this example, would just be 2 radical 2, 2 square root of 2. There's nothing else we can do there. Again, since the square root of 2 is irrational to begin with, if we have 2 times as many square roots of 2, that'll still always produce an irrational number. So the answer to this is never rational again.